All right, let's continue our discussion, okay? And let me also share my screen first. Okay, oh. Okay, so far, when I'm talking about the regression analysis, okay, the regression equations, which I uh, covered, is called the population regression equation. Population regression equation. Okay. And now I'm going to talk about estimated regression equation. So showing on the diagram. Okay. And if I can represent all these points as the population. So actually the one we just explained it, y equal to beta 0 plus beta 1x plus epsilon is what we call the true relationship among those population, I mean the points. Okay, but most of the time we don't have the population. It's not easy to get the population. Okay, so actually we are collect the sample. Okay, so now if I'm saying that those points are what I collected the sample from the population. And when we say the sample, and in this class, when we talk about those data, actually we are really saying that this is a good representative. It's a good sample, means it is a good representative of the population. Okay, so using those data, I'm trying to find an estimated regression equation, which is the red line. Okay, then without knowing the population's regression, we're trying to use the data after we collecting the data, and we estimate this regression equation based on the sample to represent the true populations. This is usually all the statistics is talking about. Okay, since we are not able to get the population, we just get the samples. Okay, no matter how big of the sample, nowadays we're talking about the big data, right? If the data is big enough to represent the true population, then maybe there's another area to talk about the relationship between X and Y. Okay, if we don't have the true populations, or although the data is big, but still it's not population. Therefore, those technique of collecting the data and using the data to estimate or describe the population is always important nowadays. All right, so this is 1.3. We're going to talk about this one. Okay, so this is okay. Okay, once a specific equation has been decided upon, this means specific equation means the relationship between x and 1. Okay, it must be quantified. Okay, this quantified version of theoretical regression equation is called the estimated regression equation, and is obtained from a sample of data for the actual x and y's. In other words, the estimated regression equation has actual numbers in it. Okay, let me show the examples. Okay, this is according our textbook. Okay, this is the relationship in equation 1.12. This is called populations regressions, the relationship. Okay, then 1.13 is after we collecting the sample from X and Y, and we are using some statistical methods, which we are going to explain it in chapter 2. Okay, this is the technique we use. Okay, then end up with some numbers. Okay, this is equation 1.113. What's the difference between 1.12 and 1.13? What's the difference? So thinking about this one, right? This is the red. 1.13 is the red line. Okay, 1.12 is maybe, maybe it's not real. This is still data, but thinking about the relationship, thinking about all the points, this is some subset of the population, right? Since it's the data. So you can imagine if you have more data, then you can get something like population. So all these dots, not only those one, but also more, okay? But the relationship is something like this way. So 1.12 is the population relationship between X and Y. You can imagine on your mind. Then 1.13 is we collect those data. Then we end up with this one. So what's the difference between these two equations mathematically? Look at these expressions. What's the similarity and what's the difference? Can all of you hear what Max say? You like to use some?
Yeah, what I'm trying to explain is if you look at equation 1.12, it looks at the whole population. Let's say, for instance, if you collect a data for CYCU, if we have like 15,000 students, but equation 2, which is 1.13, just collect the exactly number that you collect, like the sample that you collect, let's say the square root of the xi. But for equation 1.2, you can see that it has an error term, but equation 1.13 does not show any stochastic error term.
All right. Look at this one. Only the similarity is the X, right? And we do have some other notation put on the Y, on the top of Y. We call it hat. It looks like we wear a hat. Okay, so usually the expression is like this one, Y hat, and equal to the numbers, right? And this is really the estimate from the data. So this is also being estimated. Therefore, we put the hat on the beta 0 and also beta 1. Okay, then this one is actually, we put another hat on this one. The notation in our textbook, sometimes they're using this one and sometimes they're using this one. That's why I'm put these two together. And actually either this one or this one denoted as the residual. What do we mean by residual? Residual is using the actual. This is the data we collected, right? And y hat is based on these equations. As long as you put the x in, you can get the y hat, right? So just like this way. If I have, let me put this dot as big as possible, okay? This is one dot. Means what? Means I have the x values is like x1. X1 means some numbers, okay? All right. And after I put the numbers of x into this equation, just like 113, okay? And if I have the x numbers like this one, then I multiply 6.38 plus 103.4. Then I will get the numbers, which is y hat. So in other words, where is the y hat? Is on this one. This is the y hat. Okay? Since I put this x in, and this is the equation of 1.13, and I multiply 6.38 and plus the intercept or constant, then I will end up with the numbers, which is y hat. But actually the y is here, right? You see what I'm saying here? So there's a difference. And this is what we say epsilon I, or we say is EI, which represent the error terms. And this estimation of the error terms is called residual. Okay? Understand what I'm saying here? So whatever estimate in this regression analysis, especially on this book, we put the hat on it. So we put hat on it for the beta 0, we put hat on the beta 1, we put hat on the y, and we also put a hat of epsilon. So only xi is the original collected data. So that's why I'm saying that given x, so x is always given. After we collecting the data, x is always given. Then after we have this one, we have this relationship, then we'll end up with the y hat. And the y hat will be the difference from the original one. So in this case, residual is using actual y minus estimated y. Okay, in this case, the actual y is here, estimated is here, so the residual is positive, right? Okay, this is the positive relationship. Then let me use this dot, which is the letter, the lower part of this line. Okay, actually the value of x is x2. Okay, then this is y2, is the actual y. This is y1, this is y2. Okay, this is the actual y2. But if you plug this number of x2 in the equation, actually y is here. So y2 hat is here, right? Okay, and using y2 minus y2 hat, what's the difference? The sign is negative. So for the residuals, it can be positive, it can be negative. It depends on the site Now, points falls on which side of the equation. If it is above the line, the residual will be positive. If you're below the line, the residual will be negative. So residual can be positive or can be negative. Is that clear? Okay, I'm really sorry that those students on the teams cannot show what I have it, on the blackboard. I hope you all understand it. It's pretty clear. It's more clearly if I can show something on the board, right? Okay, so let me explain this one. Okay, so residual and can be expressed in this way. Did you all remember these parts? These parts? Actually, this part is equal to the y hat. So y hat is the expected value of given x, the expected value of y given x, and which is a deterministic components. Okay, but the arrow terms is always change, can be positive or can be negative. So we say that the arrow term is a theoretical concept that can never be observed, but the residual is the real world value that is calculated for each observation every time a regression is run, and the regression can be thought of as an estimated of the arrow terms. Okay. Oh, this is, without this basic concept, I think you have to know this concept in order to understand regression analysis. Okay. And what I'm saying here is all in the textbook. So that's why I'm saying that reading textbook carefully is important because this is an introduction textbook. It's not very difficult to read. And the English, I mean, this book explain the mathematics relationship using very simple and friendly English. So I hope you can enjoy this book and read this book carefully. Okay. And let me also explain this one. Okay. And most of the regression techniques not only calculate the residuals, but also attempt to compute the value of beta 0 and beta 1. Okay, that kept the residuals as low as possible. Since the residual is the difference between actual one and the estimated one. So if this line is close enough, okay, is close enough, the relationship between x and y, then do you think the residual is smaller than expected, right? So we wanted to, the regression analysis is also to compute the beta 0 hat and beta 1 hat and keeps the residual as low as possible. It means that the smaller the residuals, the better the fit and closer the y hat will be to the actual y's. Okay, and this is what we are going to talk about, the theoretic parts to how do we do this, how does that, what kind of a technique can let us to achieve this goal. Okay, And, it's always easier to explain it using just one X variables, but all this uh, idea can be extended to multiple regression analysis. And, even the X variable is more than one. So actually, if it is just three, this is K variables, right? Then again, this is the populations, and this is the estimated regressions. So we put the hat on Y's and all the beta 0 and all the beta 1, all the beta variables in front of X variables. This is called beta coefficients. So we have K beta coefficients. Then the residual, again, is just only use the actual Y minus the estimated Y. All right. So this is the diagram, okay, which I show on the blackboard. But actually, if you look at textbook, okay, this is, look at this one. This is the dot, okay? According to this chart, there's a positive relationship between X and Y, right? Look at all these dots, okay? And the dashed line, look at this dashed line, okay, is the estimated line. So it is, the symbol is like this. Put all the head on the Y, beta 0 and beta 1. And they do, show the so-called, this is what the expected Y given X. So this is the deterministic parts, okay? And the difference between the actual one and the estimated one is the residual. I think this diagram is similar to what I have it here. Now this is in the 1.3. All right. All the explanation. I think we just stop here. And we have two examples. Okay, we are going to show the examples to all of you, and then show you how to collect the data, how to estimate the regression. So any questions so far? Any questions so far? No. All right. If you don't have any questions, let me go on to have our examples. Okay. And okay, so this is the example. We call simple regression model, and it's on page 35. So if you have textbook, this showing the example, and the data is HTWT1. So let us use the data first, okay? All right. So since I have this data set, let me explain it, okay? How to use the Excel to move into the eViews, okay? Although I still can use the eViews data, but I'm going to, later on, most of you need to use the Excel, then use the eViews program. Therefore, you need to transfer your eViews, Excel's data into the eViews forms of data, okay? And you'll know that this is the update version of Excel. And what you downloaded from our data set is the old version. But either way, I think it's okay. Okay, let me, if you want to uh, store it as an updated Excel forms, it's okay too. Okay, and let me show. Okay, this is the Excel. Okay, the data from 1 to 20. So we had 20 data. Okay, 20 observations, and X and Y. What's the definition of X and Y in this example? Let's see. Okay, let me see the, okay, let me explain this first, okay? If you want to store the old version of Excel into the latest one, you can just use this one and store to another new form. No, I'm sorry. Am I right? Okay, choose the function which is this one, Excel. Okay, the top one. Okay, now I have the version is this one, this version, but which is an old version. Okay, if you choose the top one, will be the latest version of Excel file. So if I do this one, okay, I store it. You may like to see that I have another form which is similar to this one. This is the latest version of Excel, and this is the old one. But I think either you use the latest one or the old one, you can transfer this into the eViews. I don't think there's any problems. Let me just try that, okay? Well, okay. After you install the eViews, you should have the icon, something like this one in your computer, right? Do you? You should have this one. So you turn it on. What's wrong with it? Okay, I like to move. Register components. What do you mean by that? I just say yes. Okay, I like to move this one a little bit further. Okay, you can open the eViews. Okay, then draw this one in. Okay, then next step, then finish. Then you have this. Just draw it in. Just draw it in. I'm just using the old version. Okay. Then you have this one, and this is the eViews form. And if you want to set up a file, then you can save us. Then make it and using this one. And in this case, you stored it. Okay. Then you do have another eViews with the name on it, which is the same as this one. Okay, and this one will be exactly as the one you turn this one on, and if you choose the eViews, and this is the same as what I have here. Okay, so you can choose either, eViews form to transfer into the eViews, or just select the eViews form of data. Either way. Okay, so since I have already have it, okay, let me show how to do it. Okay. First of all, there's so many functions, okay? And I'm not going to talk about all of them, okay? I just show you what do I need in this class, okay? So for example, if I want to see the relationship between X and Y, okay, I think we need to understand the definition of the data first, okay? If you have the books, the table 1.1 is, I think I have it. Okay, I mean, this is the data from table 1.1, and this is actually what I have. And the height here is X variable, and weight is Y variable. Okay, and what's the height and weight definition here? Is 20. Okay, Y is weight. The measurement units, okay, the data they collected is using pound. Since this is American books, okay, so they're using Western way to measure the weight. In Taiwan, we're using kilogram, right? Okay, I don't know whether you're in your country, but in this data set, so the measurement units is very important. Okay, for the data, the measurement units is very important. In this case, Y is the weight in pounds. Okay, and what's the X? You should be very careful. Okay, the height and in inches. So means the definition is inches, but it is above 5 feet. Okay, in Taiwan, the height we're using centimeters. Usually in the Western style, they're using feet and inches, right? And this X variables is the height in inches above 5 feet. So what you have from the data set, like, for example, this is 5. The first one is 5, means what? Means this person is 5 feet and 5 inches. Okay? 5 feet and 5 inches. So it's 9 inches to 13 inches, etc. Okay? So this means for this example, okay, actually this is a game. It's a game, okay, to forecast, to predict a person's weight. Since this is X variable, this is Y, right? They're using height to predict a person's weight. Okay, and they are just saying that if the actual weight and the predicted weight is within some certain range, then if it is small enough, means within some certain range, then you will gain $2. But it is beyond the certain range, then you lost $3, etc. Okay, this is the prediction of the weight according to the height above 5 feet, and they are just using, they're randomly choosing 20%. Okay, all right. So actually, this is not, this part is what after we do the estimation and we know these predictions, y hat. Okay, after we have y hat, then we have residuals. then we know that we'll gain or lose the money. So for actual data, this is X and this is Y. Okay, so you'll see that for eViews, okay, what we have only the data. If we see from, I think we see from the Excel file is more clear. Okay, you have the X and Y only. Okay, X and Y only. All right, so I'm sorry, what happened? Okay, then how do I use eViews to predict? So look this one. Okay, look at carefully. If you don't know how to use eViews, maybe some of you already know how to do it. Okay, always hit the Y variable first. Okay, so I'll hit and use the control key. And start with Y, X. Okay, then hit the right hand side of the function and open it as an equation. Okay, then you'll see that there's a Y, X, and C. So C means constant. Y means Y variables. X means X variables. So far it's very easy. Even you type it, it's okay. But in the future, if you have a lot of variables, okay, it's better to, like the way I did, hit the Y variable first, then all the X variables. Okay, then after that, did you see the methods here? Okay, this one, if you draw down all this, there's a lot of methods. Okay, in this semester, we're just using this one. Okay, then the second semester, next semesters, we will use some other functions of this. Okay, so you'll know that there's a lot of methods. Okay, we're not able to cover all of them, but some of them which is more useful for your thesis. Okay, and this semester, since this is just introduction, and we need to build up the solid foundation of the regression analysis, we just started with using the most popular one and pretty useful one. Is the first one. It's called least square, which the theoretical parts is going to cover in the chapter 2. Okay, now I'm just showing how to do it. Okay, without selection, since this is on the first top options, so it always shows these methods if you don't do anything. And this is the method we are going to use this semester. Okay, all right. And did you see the samples? Make sure you have all of them. Means I have 20 observations. Okay, 20 observation. All right. Then after that, and I hit OK. All right. This is the output. This is the output you have. Okay. And look at this output. Dependent variable started from the beginning. Dependent variable Y. Methods is least squares. And there's a date on it and the time on it because I just run it on 10:45. Okay, so in the future, if you do your assignments, then I say that we have to do it. I will tell you in advance. Okay, you can sort of prepare it by yourself at home, but you have turned it in the class, right? Then whatever you do from your homework or assignments, okay, and this is the result you run, and it show the time. Okay, so if I read your assignments, I know that when did you do this homework. I don't mean to to know when did you do your homework, but the output shows what time do you do your run this data. Okay, so do not copy others. Okay, this is, I'm trying to say, because before I do, it happens to the students. It just cover other students' homework. Okay, there's a time. And they also show the samples is from 1 to 20. Okay, included observation 20. I think this information is very important to all of you, right? Then this is the output. Then we have variable X and C. C is called constant. Did you see the coefficients? For X is 6.377. Okay, let me write down the equation here. If this is positive, right? So let me write it down using. I think you will expect this is a positive relationship. Why it is positive? X is the height, right? Y is the weight, right? So the taller usually is heavier. Usually, not always, but usually, right? So, theoretically, there's a positive relationship between height and, so this is the weight and this is the height. So they have this positive relationship. And the constant is 103.3971. So so the diagram should be like this way. And the constant means this part. This is called intercept, right? Okay. And the slope, this one, the slope is 6.377. So this is positive relationship. Okay, so I have all this 20 dot here. I have 20 dot here. But the estimated line here is y hat plus equal to the intercept 103.39 something, right? Plus 6.377 x. This is estimated regression, estimated equation. Okay. All right. And let's see, any diagram I can see? Can I see any diagram here? Graph? Do I have this graph? Okay, okay. If you want to see the graph, okay, I can use the quick. Did you see the function here? There's a quick function at the top of it. I can use the quick and I choose the graph. Did you see that? Graph and Y and X. Okay, then what kind of graph do I want it to see? Usually for the regression analysis is called scatter diagram. Scatter. No, this is called X and Y lines. Am I wrong? Okay, then let me try it, okay? Is XY line? Oh, no, I'm sorry. I'm sorry, okay. Delete equation. No. Delete the graph, yes. Let me draw a quick and graph XY. Maybe the scatter, okay? I'm choose the scatter. But there's no lines. You know, this is the one I showed this is the one for original one. Okay, this is the original 20 observations. And look at these observations, you see the positive relationship between X and Y, right? Where is the diagram with the equations? Where can I see that? Oh, let me see, view, graph. Let's see. It's not this one. No. Delete graph, yes. Maybe view. Equation. No, I cannot see it from here. Or where is the problem? Well, I'll figure out later on, okay? After I have this output, did you see the forecast? Forecast, the function of the forecast, okay? There will forecast, means y hat, okay? They automatically, since our y variable is y, and the forecast they're using the variable name is called yf, okay? Then I hit okay. Then I come back to my data. Where's my data? Where's my data? Excuse me. Where do I go back to my data set? Where is it? Max, do you know that? I like to go back to my data set. View. Then this estimation output. This is my estimation, but I wanted to have my original data set. Close this one. Then delete it. Well, I wanted to save it, okay? Let me save it. Then put it equation 1. Then I hit OK. All right, all right. So let's change, save it. Yes. Okay. Well, then I can turn it on again. Now, look at this one. I already have this YF. That's forecasting, okay? Let me show. And this function is called residual. Okay, after I run the regressions, they already automatically give us the residual. Let me show this one for all of you, okay? The table 1.1, this is X, Y, forecast, and residual, okay? Then I have all of them, then I can open it and as a group, okay? So did you see all of this one? X, Y, forecasting, and residual. Look at this. The data here is exactly what I have from table 1.1. You all see that? Okay. I think let me stop here for a while. Okay, let me stop here for a while, then we'll come back later, okay?